All right, so here we have our classic water in a container coming out of the whole problem. It tells us a bunch of information here. What's important is the density of the liquid. I guess it's not quite water, right? And then the area of this opening. And then it tells us constant stream, appropriate rate. So H remains constant. That's good. Amount of liquid collected in 2 minutes is 7.4 meters cubed. The beaker is over here. Beaker. By the way. Now, this is an interesting question because it just wants us to take the volume, 7.2 times 10 to the negative fourth meters cubed, and divide it by the time that they give us. Just knowing that we're not going to use 2 minutes, we're going to use the fact that every minute has 60 seconds. We're going to get ourselves a volume flow rate, 6 times 10 to the negative sixth cubic meters per second. Just easy squeezy. So what we did is we did volume flow rate is just equal to the volume over the time. All right, so we just want the linear speed in meters per second of the liquid as it exits the hole. Right now we have a volume per second. What does that really mean? A volume is an area times the amount of water that comes out. Delta X. That's what's being spit out of the hole, right? So this chunk of water with this area A and this length, delta X, comes spitting out of our hole. And that happens every single unit of time, t. We can then just realize that our delta X over time, that's what they're looking for. That's our linear velocity, v. So let's take our volume flow rate from above and we'll set it equal to the area times the linear flow rate. So 6 times 10 to the negative sixth meters cubed per second is just going to equal the area of the hole, 2.5 times v. Solving for v, we're going to get 2.4 meters per second. Calculate the height h above the hole needed to create that speed. Okay, so what's going on? Well, here there's some pressure, and that's going to push the water out of the hole with a certain speed. And here there's going to be pressure of the atmosphere. So let's take our two locations. Let's call this P1 up here. Boop, P1. P1 is P atmosphere. Okay, and it is a height h above this second location in green. So we're going to write out our Bernoullis. We're going to say P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Now, let's replace some terms. So this is actually going to be P atmosphere. And so is this. Next, we can say that the water is not moving in the container, right? The water molecules here, they're barely moving. But here, they're moving. 1/2 density times our speed that we found squared. And then we might as well just call this spot 0 and the upper spot h. So this can be big plus 0. And over here, we can fill this in as rho g h. Okay, once we simplify, we'll cancel our p atmospheres. And then we have just rho g h equals 1/2 rho v squared. Solving for h yields us 0.29 meters. Onward. Suppose that there is now less liquid in the container, so h is reduced to h over 2. In relationship to the beaker, where will the water hit the table? Well, now there's less pressure pushing that water out of the hole, right? So if our water comes out of our hole with less delta x, it will have less x velocity. It will still have the same time to hit the table because the overall y value hasn't changed. But the velocity that you're traveling in the x direction is less. The delta x over t is now going to be less because the rho g h, there won't be as much h on top, which we just solved from above. So it'll be left of the beaker. It will not go as far.